quickly as we can, give you a brief introduction to Appalachian tectonics, which forms the basis for an understanding of why the topography here that we have today is anomalous, and it can't be related to the topography that was generated when the mountains first formed, or the crust that underlies the mountains first formed. Okay? So, next, please. Yeah, I'm waving it around too, I know. Okay. The thing that you, as astronomy aficionados, probably understand better than any other scientists is time. And the time scale that we work with here as geologists is the geologic time scale that goes back to the beginnings of the Earth. And it's my understanding that astronomers say that the universe is 13.7 billion years old. Well, we figured out that the Earth is about 4.567 billion years old, to four significant figures. That's pretty good. We used to say it's between 4 and 5 billion years old. Now we can narrow it down based on pretty good isotopic dating to this number right here. So you realize that when abundant life first came about, and we started seeing abundant fossils in the geologic record, where that enabled us to understand a lot of things we could not understand before. Something like 3/4 of geologic time had already gone by. And there are fossils back before that, but they're not abundant, and they don't tell us as much as those that came along subsequently to that. There is an event, we call these orogenies. These are mountain building events that occurred at a billion years ago. That must have been one right there. Yeah, a more recent one. Yeah. This formed a supercontinent, and the last event in the Appalachians, we call it the Alleghanian, or it's been called the Appalachian orogeny, formed another supercontinent. So in between, we have a lot of things going on that form the Appalachians, something we don't usually see in other mountain chains. It took 3 events to form the Appalachians after the breakup of the supercontinent that formed a billion years ago. So these are the events that formed the Appalachians, and here ending about 260 million years ago. And then there's this other thing, this recent uplift event that occurred way up here just a few million years ago, that's probably responsible for the present day topography that we have in the eastern US, eastern North America, probably in Britain, Scandinavia, and other places around the Atlantic Ocean as well. So we'll look at some of these things later on. Okay, so let's move forward here. Okay, plate tectonics is the paradigm that we have in geological science. It came about initially as continental drift, which many geologists did not accept, because they, especially in the northern hemisphere, because we could not see connections between, say, North America and things in Europe. The southern hemisphere geologists accepted it right away because they could see things on both sides of the Atlantic that said, sure enough, these were connected. But in the early 1900s, the idea of continental drift was set down for the first time, even though it was thought about and speculated about before that. Then in the mid-30s, a guy at Princeton named Harry Hess wrote a paper in which he just basically laid out the principles of plate tectonics. And the paper was not widely read or widely accepted, and so he sort of remained in the background, even as a well-known geologist, until till the 60s, and some seismologists got together with using oceanic data, earthquake data, a number of other data sets, and put together the concept of plate tectonics in a single paper published in 1968. And that's when the rest of us started learning about that, and we became we realized that we now have a basic paradigm that the physicists had in the late 1800s in atomic theory. The biologists also had in the 1800s. It took us until the mid-1900s for us to have anything like that, partly because of the lack of critical data. Okay? So plate tectonics is a principle that involves the generation of ocean crust at mid-ocean ridges, like right here in this cartoon, and then the destruction of ocean crust in the oceanic trenches, or we call them subduction zones now. The continents are merely scorekeepers. They float around, they're lighter material, so they don't go back into the mantle. And so, but it's fortunate we have continental crust because it records information about Earth history going back 4 billion years. So it's a very good thing to have. But it's a non-essential component of plate tectonics, really, in that regard. The oldest ocean crust we have today is 200 million years old. And so if we didn't have continental crust, we would not have a record beyond 200 million years right now. Next, please. Okay, this is the present-day plate configuration of the Earth. Several large plates, and then some small ones like Caribbean, Scotia, and some that have just about been swallowed up off the west coast of the U.S., Central America. Nazca is a fairly large plate, but it's going into South America, and so on. So these are the major plates on the Earth now. Next. Okay, something else that's an integral part of geologic reasoning. We teach it in Geology 101, but you can teach it in using the principles of thermodynamics if you want to, and other things that are embodied in this so-called rock cycle. If you start out with molten rock material, we call magma, and let it crystallize, okay, one of the things that comes out is igneous rocks, the products of crystallization of magma, or volcanic rocks if they come out on the surface. But also gases and water are produced, which interact to produce, they first of all produce the atmosphere and hydrosphere, and then secondly they interact to produce the biosphere. That's what these side events are. But then igneous rocks will weather, and they get eroded and transported, deposited as sediments, which get stuck together in some way and form sedimentary rocks, which then might get buried, or they might get recycled into weathering again, and come back through the cycle again, a short cycle. Or if they're buried deeply enough, they start to recrystallize and we call it metamorphism, and it's in two forms: regional, which is over large areas in contact next to igneous bodies, and then they form metamorphic rocks, which can be remelted into magma again. So that completes the main cycle. So this is the geological rock cycle. So this is another integral part of geologic thought, even though we don't talk about it so much, except maybe in Geology 101. But it's a principle that's embodied in a lot of the things that we do. Next, please. Okay, another cycle, which we call the Wilson cycle, was first proposed in a paper in Nature, about a 4-page paper in 1966 by a Canadian named J. Tuzo Wilson. That's why it bears his name today. It really is the opening of oceans and then the closing of oceans, okay? And so his paper was entitled, "Did the Atlantic Close and Then Reopen?" And he laid out the ideas of that. He didn't really talk about a cycle in that sense, but that was the concept that he was working with there. And then there are all kinds of variations that can take place in how ocean opens, and then you get subduction zones that eventually close the ocean and collide continents or even island arcs and this sort of thing. Next, please. Okay, the Appalachians. These are the southern, northern Appalachians, and in Newfoundland things go out to sea, and features that we can see in the North American Appalachians we can recognize in Britain, We can recognize features in that carry on into the so-called caledonides in Scandinavia. They have counterparts in Greenland. And then in Western Europe, we see other features that carry right on through into North America as well. And of course, North Africa, or Gondwana, if you wish, has components in North Africa as well. So the Appalachian mountain chain is really just one part of a major mountain chain that went through these three events that I mentioned a minute ago. And ended up with a huge mountain chain. Of course, this formed the supercontinent Pangaea, and that was a thing that happened that was the culminating event in the Appalachians, but it was also the same in the mountains in Western Europe, which are now buried in many cases, but also the Ural Mountains in Russia formed at this time, following three major tectonic events. Next, please. Okay, we start with the supercontinent, as I mentioned earlier. This is the one called Rodinia that formed 1 billion years ago. I have two different configurations here because of a lack of complete data, less complete data sets. There are actually 4 or 5 models of how Rodinia might have been put together. And then Rodinia broke apart, and then 260 million years ago or so, Pangaea formed, another supercontinent. We can put it back together pretty well, actually. And so then, of course, it broke apart to form, the continents moved into their present configurations over the last 200 million years or so. The interesting thing about the formation and breakup of supercontinents is that with Rodinia, it took Rodinia 250 million years to break up once it formed. With Pangaea, it only took it about 40 to 60 million years to break up. We don't know why. We don't understand that process very well. And so people talk about the supercontinent cycle, but in terms of it being a real cycle that we can define and look at the beginnings and end points, yes, we can see these things happening in the geologic record, but we don't see what really causes a supercontinent to break up once it forms. We don't understand that. So we begin with Rodinia, and we end up with Pangaea, and in between we form the Appalachians and the European equivalents of the Appalachians. Next. Okay, well, this is just another way to look at what I was just telling you. Here's a time scale on the bottom, and then these are events distributed throughout the time scale. This is Rodinia here, break up Rodinia, form several oceans out in between the different continents that opened up when Rodinia broke up, and then you start to close them one at a time. And there is these orogenies I mentioned on the time scale there, the Taconic, and the Akkadian or Neo-Akkadian, and then the last one, the Appalachian or Alleghenian orogeny. Yes, Dave?
Was there a Gondwana?
Gondwana is the conglomeration of all the southern continents. Okay? So, and that formed actually about, sort of after Rodinia broke up, about 500 million years ago, 540, something like that, Gondwana began to consolidate as well. Okay? And so then finally, Pangaea broke up, as we've said, forming the present Atlantic Ocean as the continents moved apart. Next. This is my thing here. One of the things I have looked at throughout my career, I didn't know at the beginning I was going to approach it this way, but I ended up doing it this way, is while I've worked in the Appalachians most of my life, all my life, I also have gone and looked at other mountain chains, such as the Alps, the mountain chains in Britain and Scandinavia. I've been to the western U.S., western Canada, been to the Andes in South America. And I like to think about how different mountain chains form and how they're similar and how they're different. And as a result of that, most geologists can tell you they have different components to them. And then so I just decided, well, I'll put a model together. for an ideal mountain chain, if you wish. And so my attitude always is, if you don't like my model, build your own. So that's what I've said up here. Next. Okay. One of the things that we see in mountain chains is a lot of curved features. In the Appalachians, we see that with these great arcs that are pointed into the interior of the continent. They're convex into the continent. We see these things in mountain chains, and we see these big faults that separate different parts. And I guess I need to tell you, you think this might be a space photo, but actually it's a photo of scum on a lake. This is a photo that I took on a windy day when I was out with a graduate student on Altoona Lake in Georgia, and we walked around a small cove, and all this beautiful stuff was moving around and forming these arcuate features. And I told him, well, this is a model mountain chain here. And so I shot a whole roll of, this is back when we shot film, I shot a whole roll of film there, I think, in that place. And this is one of the better pictures that came out of it. There's a piece of aluminum foil floating there, maybe a piece of styrofoam there, and so on. Next. Okay. The Appalachians then, from Newfoundland to beyond Alabama, this is Florida down here, have a whole bunch of different components in them. I'm not going to go through these in detail with you. What I'm going to do is to show you some of the things in small pieces, rather than going through the great details that we could on trying to understand the Appalachians. But so I'm going to give you a very cursory understanding, and I'm glad Dave interrupted me to ask a question. If any of the rest of you want to ask a question or Dave ask more, please do so. Okay?
I have one, Professor.
Sure.
Before we get too far afield, I was wondering when you were saying it's not known about why it takes such short or so long time to break one of those two supercontinents.
Yes.
I'm wondering if the tidal forces has been looked at seriously as Earth approaches perigee, for example.
Yes.
Okay.
Yeah. It's just like back in the 90s, I guess it was, there was a meteorologist who suggested that all of they were going to get maximum tides occurring that would produce major earthquakes. And of course, he picked out New Madrid as a place where there might be a major earthquake very soon. That was all dismissed back in the 20s. And so it's really not a viable concept, I don't think. And, people have asked me about, well, when you get all the continents together on one side of the Earth, doesn't that upset the angular momentum of the Earth? It doesn't, because continental material is light, it floats, it's very thin relative to the rest of the mass of the Earth. So it doesn't upset that sort of thing either. Another hand up there.
Professor, all of this area was underwater once upon a time because we have watered fossils at the tops of the Smoky Mountains and other parts of the Appalachian.
No, we don't have any fossils in the Smoky Mountains. No, we have them right here in East Tennessee. Right here at Solway Bridge is a great fossil locality. But go ahead with your question.
Wasn't this area at one time an anticline?
Well, there are anticlines and synclines all over the place in this area today. But that has nothing to do with the fact that what you said at first is exactly correct. There were marine inundations into the interior of North America back from 500-something million years ago up until 460. And this thing started to happen on the margin of margin of North America, where the margin began to be destroyed. That was the first orogeny. But then there was still marine deposition taking place in what's right here in East Tennessee. And so this is if you want to get into details of what went on here, that's fine, but and I'll show you some photos of some of these things here as we go through. I think I kept them in there. But yes, we had marine inundations in this area.
But what is now the Appalachians was also underwater.
Oh, well, that's true, sure. But they were underwater, then the oceans receded, then they were inundated again, they receded, they were inundated again. The coal-bearing rocks on the plateau just west of here they're part of a great delta. that formed when the Appalachians were being uplifted and erosion was taking place. So you can go into that as much detail as you want. Okay. So this orange area out here are the coal-bearing rocks in the western part of the Appalachians. And then the yellow area in here is a group of sediments that formed during the time of uplift again, farther back than that, at 360 million years ago. We see some of that down here. It's not as visible on this map. And even before that, at 460 million years ago, there were other sediments being fed into the interior, into the marine environment there as well. So, and then one of the things that happened also is that there was, in the middle Paleozoic, about 360 million years ago, there was a chunk of ancient volcanic material, essentially dead, but it was volcanic in origin, but the origin was 600 million years ago, that collided with eastern North America, that preceded the great collision of Gondwana with North America at about 300 to 260. So there's a lot that went on there, and what we're going to do is to gloss over many of the details here tonight. Next, please. Yeah, okay. One of the things that you get in mountain chains is abundant faults. Not that happen this way necessarily, as on a tennis court, but faults are fractures, okay? They're at the latitude of Knoxville and Oak Ridge right here, there are actually 10 major faults across the valley of East Tennessee. They're not active. They've been dead for 260 million years. But we can recognize that they're faults based on the repetition of units we know the ages of. Next. Okay, there are three basic types of faults. This is the basic anatomy of faults. This we call the hanging wall, this is the foot wall. In this case, this block is moved down, so we call it a normal fault. The same block, if it moves up, we call it a thrust fault. It used to be called a reverse fault because it went the other way. And then there are two kinds of strike slip faults. One is right-handed, the other is left-handed, depending on which block is approaching you. The San Andreas fault is a right-handed strike slip fault. So the way you remember that is LA is on the west side of the San Andreas, San Francisco is on the east side, and so one is moving toward the other. So conceivably, a few million years from now, LA and San Francisco will be next to each other. This fault keeps moving. Of course, the populations will probably take care of that before that happens. Okay, next please. Okay, this again, illustration of different faults. Many of you know Bob Olson here in Oak Ridge. This is the hanging wall above his head, his foot wall. The foot wall is the place where he has his feet right now. These are all miners' terms, actually. And the actual fault zone is right there. It's about, in this fault, it's about 18 inches thick, 18 to 24 inches thick or so. Very distinct fault rocks that we find in those fault zones. Next. Okay, regarding faults, we have two different kinds of behavior, maybe sometimes on the same fault. Even the San Andreas exhibits both kinds of behavior. One we call stick slip, the other we call stable sliding. Stick slip produces earthquakes because things lock up and release elastic energy. Stable sliding involves continuous motion. I think some of the seismologists are now calling those slow earthquakes, but it's stable sliding. We've known about that for a long time. So what you want is an earthquake-free fault zone that would continuously move and relieve accumulated strain energy, but you don't get that many times. What you get is accumulation of strain energy and then stick slip type behavior. Southern California is locked up now. Central California is moving. Next. Okay, here's the San Andreas. Gulf of California ends about right there. The fault is on land there, and it goes back out to sea in Northern California. This is the Cascadia subduction zone up here off Washington and Oregon. You can see this thing. I mean, this is something we can see. Earthquakes in the eastern U.S. don't generally break the surface. And we don't see that, we don't see the fault actually at the surface. San Andreas we certainly do see. It's also a plate boundary. This is North American plate, this is Pacific plate here. Next. If you don't believe, you can see the San Andreas Fault, fly over it sometime. This is it, out east of LA. You can actually get the displacement off the creek right there. You can see the fault there has displaced the creek that way, so you know this side's moving towards you, so it's a right-handed or right lateral strike slip fault. Yes?
I guess I'm a Californian, and I have the impression that a lot of California are terrain that has been swept off with other things.
Well, that's true in Northern California and actually east of the San Andreas, yeah.
So you don't really see the plates there. You know, a lot of the land are things that have been added to a plate that maybe is in Nevada or something.
You go back far enough in geologic history, you can pick out things like that. That's right. But the present-day plate boundary is a clear boundary, though.
Yeah.
This is North America. This is Pacific Plate over here, and here's an orange grove, and you can see the San Andreas going right through it, and you can figure out, you know, in real time how fast it was moving. Of course, this is in Orange County, California. So, what's there today?
Houses.
Houses, right? Yeah, exactly. Next. Okay, back to our Appalachians again. So this is, I'm not going to talk anymore about this. Let's go, move on, please. Okay, and again, my tectonic map. We're going to look at different parts of the Appalachians and in a very hurried way now. Come on, let's go. Okay, old rocks. The oldest part of the Appalachians. Could I go back one, please? Yeah, the red blobs right all through there in the southern Appalachians, in the central Appalachians. Here are the Adirondacks, not in the Appalachians, but the Green Mountains in Vermont are right there, and the Berkshires in Massachusetts and so on. And up here you see another green piece. That's the Long Range Mountains in Newfoundland. These are composed of old rocks that got caught up in the Appalachian events. We call this basement. And this material is underneath us right here. It's not deformed here in the Appalachian events. And if we don't have any drill holes or many drill holes that go to it, so we don't know a lot about it except from indirect data. Yes?
I was wondering if you could orient me on this figure. I'm having a hard time telling exactly what I'm looking at. Look at it from above, or is this a...
Oh, this is a map.
Pardon?
It's a map.
Seen from, okay, from above.
It's a map.
Which
Yeah.
would it be, north and south and so on?
North is that way.
That is-
It's on its side so we can get it on on the image here. Yeah.
I wasn't sure.
Yeah, no, that's fine. Yeah, we're located right here.
And
Okay?
that orange stuff is that the Cumberland Plateau?
Uh-huh,
Or is it
yes,
northern?
yes. No, it's the Cumberland Plateau called Allegheny Plateau farther north. Yeah. Next. Okay, old rocks again. These are over in North Carolina, very close to each other. This is a toxoid gneiss, it's called, but it has an age of 1.15 billion years, abbreviated GA. Next. We always thought that these were North American rocks until people started to do lead isotope work on them. I stuck this in because I think it's very interesting. That here are, you can see the Adirondacks, Llano Uplift in central Texas and West Texas. They all plot on a North American curve. Our central and southern Appalachian old rocks plot on a Brazilian curve. So those rocks really are exotic to North America. They got here a billion years ago. They got caught up in the Appalachian events, but they are, even though they look like rocks in North America, they didn't come from North America. And a lot of people have difficulty accepting that. But the isotopes tell you pretty clearly, two curves here, one for Amazonia, the other for North America. Next. Okay, we're going to move on. Some of the red blobs are the old rocks. We're going to move into the interior and look at some other things here as well. Next. When Rodinia broke up, this is a section, this is a vertical section like a big road cut, but it's taken out all the deformation. And so I've restored this to where what it might have looked like. It's basically a cartoon, realize. But here are the Great Smoky Mountains, and here, this is Cartersville, Georgia, here, Roanoke, Virginia, here. Okay, you have this great thickness of sediments that eroded off the continent when there was a mountain chain there, when Rodinia was breaking up. Okay, there's as much as 15 kilometers, over 40,000 feet of sediment that we figure is in the Smokies. A lot is eroded away, of course, but we can reconstruct that. Then sitting on top of that, we have some other younger units, and what these tell us is that this is a so-called rifted margin, and then sediments deposited on the rifted margin that became more consistent, and then finally carbonate rocks were deposited there, which means the ocean was completely open, like the Bahamas Bank today, like the Great Barrier Reef today. Okay? Let's move on, please. Okay, these are some of the rocks that we see in the Smokies. This is up on the Clingman's Dome Trail. I have some of my former graduate students sitting there. And then these are the same rocks again, a lot of variation in grain size. These are just sandstones, and coarse grain, fine grain, and so on, alternating, but huge, thick beds of this stuff, rapidly deposited. Next. Okay, this is some of the finer grain material that's deposited on top of this thick sequence here, but there's some coarse sandstone interbedded with it. This is on a creek called Double Camp in southeastern Tennessee, south of the park, not very far south of it. Next. Okay, what was going on here then, this is another cartoon of mine, was that, okay, here you had the Gondwanan pieces that had rifted off of North America, and here's this rifted margin on North America, a map again, and off of Gondwana was an island arc that formed there. This is at 500 to 600 million years ago, and this becomes an important player later on because it collides at 360 million years ago with North America still, and it's separated from Gondwana. And then this piece right here of North America with its own fossils and everything, we tell clearly that's where it belonged, decided to leave North America and ended up in Argentina and Bolivia. And the paleontologists knew about this for a long time. Those tectonic types didn't catch on till about 15 years ago. So, but anyway, this was a configuration of the continent with a big ocean sitting between, and it opened as Rodinia broke up, but then this started to close after that. Next. Okay, I'm going to take you to a place on the South Carolina-Georgia border on the Chattooga River called Woodall Shoals. This is a place where the rocks were deeply buried. These are equivalent to the rocks in the Smokies, but deposited much farther east of there and perhaps on ocean crust. So, next. Okay, this is a panorama that I shot there, a big exposure of rock there, beautiful exposure. We learned an awful lot from studying this place over the last 25 years. Next. Very nicely folded rocks, but again telling you that the rocks were deeply buried because of the plastic nature of the deformation here. Next. And then even layers, this is the same place, layers have gotten pulled apart and then individual pieces rotated. If you had to put that back together again, which it was an individual single layer at one time, I realized what you have to do. You have to rotate each individual piece. These are called boudins or sausage, and rotate them and then fit the pieces together, all in the plastic realm. These rocks were more plastic. These were more brittle or stronger, but still plastic. Next. Okay, and so this is what happened during the early Paleozoic or 460 million year old event. Here's our island arc that's now dead, that moved away from Gondwana, and then here are island arcs that were formed next to North America and then were pushed up on North America during this event that closed this ocean in here. We have other oceans left out here that did not close until later. That's the key of this Appalachian history, I think. Next. Okay, something else that happened at this time too was the thing that we saw going on in what's now the Piedmont is something that went on that affected rocks and marine sedimentation and other things over all of eastern North America. And actually we found evidence of this in Sweden and other parts of southern or western Europe. These are dots indicating thickness is measured. But you see right here in Tennessee, this is, we have these things. This is volcanic ash. And we, for a long time, really have never known where that source was, even though the person that drew this diagram thought it was out here. It had to be because of the thickness. Well, all this material was brought in collision of island arcs. So we now have figured out what this was and where it was. And we think it's rocks of the same age. We know the age of these volcanic ash beds. If you want to see one of them, go down behind the new car wash at the corner of Illinois Avenue and Turnpike, walk out behind there and look behind the retaining wall. There's about a 3-foot thick volcanic ash bed right there. Next. As a matter of fact, there it is. That was before they built their retaining wall. Again, Bob Olson for scale. And he's a good average person to keep putting a picture. And then this is a close-up of the same volcanic ash bed. Next. Okay. Something else that formed and after the 460 event was a feature we call the Brevard Fault. It comes all the way up from Alabama into Virginia, and we trace it. It dies up in Virginia somewhere. And this is a big fault. Some people have said it was a suture. Well, we know now it's not a suture, that the same rocks of the same age occur on both sides of it, but yet it had a long history of movement. It moved several times, something that most faults don't do. That is, they don't move and stop and stay dead for millions of years, then they move again. They don't usually do that. They move once and they die. This is what most faults do. Next. This is a quarry over south of Asheville, and this is the actual fault contact with the Blue Ridge. There's a Euclid truck right there, if you can see it for scale. That's a single fault surface right there. This is a piece of carbonate rock, though, that's identical to carbonate rocks right here under us right now. And this had to be brought up from below into the Brevard Fault Zone. Next. And this is what some of the carbonate from the Brevard Fault looks like. And I think I'm running out of battery here. But they're smaller pieces that have been brought in, smaller than what was being quarried over at Fletcher, North Carolina. Next. If you look at this material, and oh, you got another one.
I'll replace the battery if you don't like that one. It may not be visible.
Okay, let's see. Oh yeah, that's good. Anyway, under the microscope, you see a number of things. This is quartz. This is muscovite or mica. Some graphite is in this one, and there's enough heat there to partially recrystallize much of the quartz, but still, and recrystallize the micas, but not to destroy the deformation record that's there. Oh.
This is better.
Okay, thank you. Okay, next. This is a deformed granite here. It's in the southeast edge of the Brevard Fault Zone. And this was deformed 360 million years ago, we think. And the individual feldspar grains are just smeared out, and you can see tails on them that will actually, you see the clockwise rotation on that right there. Next. Okay, this is a model that I put together several years ago from a cross-section through the Brevard Fault. The place I showed you near Asheville was at this point right here. Then there's the earlier event of movement, then a still earlier event. This was at great depths, 20 kilometers or so. And then 12 kilometers would have been this one, and then maybe 8 kilometers would have been that movement event. So if you take all these and put them down in the crust, this is what you end up with a model for that. Next. Okay, we're going to look now at an area right in here. Next. This is a blow up of the same area. Very, very complicated geology once you get this. Here's the Brevard Fault going through. The Blue Ridge geology up here and the Piedmont geology down here. And then this is an exotic terrain. It's a piece of Africa, actually, that came in the 360 million years ago time. Next. Some of the structures we see related to that are like this. You see the fold that turns around, comes back on itself, and there's a back fold right there. This is very much the kinds of structures we see in the Alps and other mountain chains as well. Next. Okay. Then this is the 360 million year old event, where here we brought in the exotic terrain. It has, the reason we know where it came from is because it has fossils in it that have that tell us that the rocks were derived from Africa or Western Europe somewhere. So, but this is the 500 million year old material that had sat off Gondwana and evolved there. Then it came across and it collided obliquely with North America, doing all kinds of crazy things. And here's our piece of North America now in Argentina. It arrived really about 420 million years ago. Next. Okay, so 340 million years ago, this might have been what the continents would look like. This is North America. This is the European side, a great open ocean there. And we're getting ready to form Pangaea right then. Next. So this is Carolina. I'm going to show you a couple of pictures of rocks from the Carolina terrain. Next. This is some dark volcanic rocks. Sorry about this is the best I could do at the time. Sorry about the ferns and moss covering most of it up. Ferns are very nice. Next. And then some light-colored sediment that are associated with the volcanic rocks. This is very typical of arc systems. Next. And then they have, these are some of the fossils. This is a piece of a trilobite. This is a part of a head of a trilobite, and that animal would have been 2 feet long.
Wow.
Probably, yeah.
Big hops, right?
Would have been a big one, yeah. And they were the first real efficient predators, I understand, from the paleontologists. Next. And then when you cook these rocks too, they begin to develop structures of the kind that we saw when they get buried deeply enough, like at Woodall Shoals, where I showed you a little while ago. Next. Okay. The external parts of the Appalachians, where we are right now, we're seeing here deformation that took place about 260 million years ago. Deformation up here in the external parts took place 460. This is related to the last collision between Africa and North America. Okay, next. And what happens is you have a big, just cold crust, big chunk of crust, as in Africa moving up over North America, similar to what's going on today in the Himalayas. The Himalayas are being formed by India going under the southern margin of Asia, essentially doubling the crust. That happened here in eastern North America about 300 to 260 million years ago. And you got a bunch of faults of material trying to get out of the way, basically. Like you're pushing snow in front of a snowplow. That's what we see here out in the valley of East Tennessee and farther north, farther south. Next.
Now, is that where we see basically the fault where I-75 goes north?
There's no fault exposed. Well, the Jacksboro Fault, which is right there. Here's I-75 right there. This is a cliff of sandstone. Okay, there's no fault there. This is just a cliff of sandstone. The Jacksboro Fault, though, goes down this V-shaped valley. When you're driving down here, getting ready to climb up onto Pine Mountain, just past Lake City, La Follette is right there, right beyond the Caryville exit, actually. And you look down through there in a very straight line, very straight valley. You're looking along the Jacksboro Fault, okay? That forms the boundary, the southwestern boundary of a big block that actually moved into the plateau at the time of this collision. This is the last fault that formed in the Appalachians going west.
But it's basically where the eastern escarpment, let's see, what is it called? Walden's Ridge basically has a big jump right there, right?
Yeah, there's this right angle bend. As you come down the interstate, you can see that.
Yeah.
Yeah, but that's the Jacksboro Fault cutting that off. And this is the, there's a basin in here that contains a little thicker sediment. And this whole block moved out relative to that. Okay? Next. And for these linear valleys that we have up in here, they relate to the repetition on big faults that were moving out just like the snowplow I described earlier. Next. And here's one of them. If you go to the, this is on I-75 north of Knoxville, just before you get to the Raccoon Valley exit. You can go out there today and see that. The big fault right there, smaller one there. Older rocks pushed over younger rocks. And of course, erosion has produced the ridges and valleys that we have today. But this fault has been inactive for 260 million years. We know it's a fault because these are older rocks, these are younger rocks. Next. And if you look at a seismic reflection profile like this old Amoco line that was run down I-95 just out of Oak Ridge here, it crossed one of the big faults there. You can actually see the fault on there. It truncates layers below it. And it's really a very, very nice model for faults all the way across the valley of East Tennessee. Next. And then here's one in Knoxville. This is at 640 and Broadway. You can see it now. There's trees growing up over it today. But again, older rocks over younger rocks, and the fault plane is right there, steeply dipping because it got tipped up. Next. And this, how would you like to live in a place like that? Man, it would be a great place to live, at least for a geologist. A nice fold there. This is on the Nolichucky River up northeast of Newport. Next. Southeast of Greenville. Okay. Then this big fault that separates the valley of East Tennessee from the Blue Ridge in Tennessee and North Carolina is a boundary that goes all the way from Alabama and it ends up in Virginia, actually off the map here. And this fault was the fault that carried all this stuff here cold and pushed snowplow-like all the rocks of the valley of East Tennessee in front of it. Okay, next. This is an exposure of the fault on US 321 at just where you go out of Tuckaleechee Cove before you go to Ware Cove. And the fault is right there. These are younger rocks. These are older metamorphic rocks, actually, unmetamorphosed rocks here. Next. And if we move a little farther northeast, we go in, this is the Grandfather Mountain Window area. Next. This is at Linville Falls, North Carolina. If you haven't been there, you ought to go there. The big fault is exposed between the little falls up here and the big falls down here. Right there, actually. Next. There's Olson again. He was sitting at the Linville Falls fault. We took that picture. Older rocks over younger rocks. Next. And there's the fault zone itself. It's been folded a little bit when it was finally being in place. Next. And these are some of the rocks out of the fault zone itself. They have various kinds of interesting structures in them. Next. And I want to show you something right here that's totally non-geologic, but it's effective what we do geologically. There are folds in here too, if you look carefully. Next. There was a guy that walked down the trail up there with a kayak on his shoulder last year, a year and a half ago. There he is coming off the falls. He put in above the falls, kayak down. There's a guy here who climbed down to help him make sure he turned the corner, and then there he is coming out the bottom. He actually survived the trip, but the Park Service was waiting on him down at the bottom there, and they arrested him, fined him several $1,000s, took his boat away, took his car away, I think. And next. They used to have this sign there. It says, "Stay behind wall." Well, to see the fault, you got to go across the wall. and get up there. Well, my interpretation of that, once I got across the wall, I was staying behind it, so I was okay. Then they put this sign up that says, if you cross this boundary, you're breaking the law. So that really affected our ability to go up there and look at geology. So I had to get a permit at the last minute last fall to take my students up there. Did so, but it was a bit of trouble, and we can go up there now and have a look at it, but most others cannot do that. Next. So this is the doubling of the crust business. Here, this is a southern Appalachian cross-section here, and a cross-section up in Virginia, West Virginia, accomplishing the same thing with a little bit different style of structure. Okay? Next. And then this is a magnetic map. As you fly over a region in an airplane, this is 3 states, South Carolina, Georgia, Alabama, and you have a magnetometer trailing behind, and it records the magnetic field of the Earth. Well, we can really get a lot of information out of that because the rocks out in here are not exposed. They're exposed up here in the Piedmont. This is the coastal plain. And then this boundary right there is the boundary between Florida and the rest of the world up here. This is Africa down here, without any question. There are fossils and other things that tell us that's Africa. So that got left behind when Pangea broke up. But there's some other interesting variations there that tell us that there's a fault right there that looks like if these two connect, these anomalies connect, this block was moving that way, this moving that way. So when Florida finally collided, it pushed everything out of there. These things were trying to get out of the way. And maybe this was the last thing to happen. We don't know. I gave a talk at a meeting on this last fall. Next. And if you this is an interpretation. There's my fault I just mentioned. Here is the suture zone, and here's Africa down here, which is Florida. Next. So what we're doing right now is we have built Pangea, okay, through a series of events. The last event was the collision of Africa and North America. And so that began some 325 million years ago, but Africa first touched in New England. These are maps now. And it touched up here and started to rotate. And there's Florida attached there. It may not have been attached if my interpretation is correct there. Then if we move again a little later, Africa rotates in, produces other faults, it propagates southward, and there's another group of mountains out in Oklahoma, Texas, that formed at this time called the Ouachitas. And then that was all over shortly thereafter. And then other events happened. Here's the collision taking place with Florida and North America, and you start to get this snowplow effect. And there you have all the faults up here in East Tennessee and north and south of it as Africa and all collided. Next. So this is Pangea. We have formed Pangea through a series of events. This is 280 million years ago. And the guy, I think, Northern Arizona, who's done these things, has done a wonderful thing for the profession to try to put these reconstructions together. Next. Okay, so we've built our Appalachians then. Now, what we'd like to do is to maybe pull them apart to make the present-day Atlantic. Next. And we want to move toward it should be not he, modern continental margin. Next. Oh, thank you. Okay, so here's Pangea, formed 260 million years ago, and it started to broke up, and to move to its present position, okay? So it's a pretty systematic breakup there. We normally think things just move straight apart. That's really not the case. One of the things we're learning today, some of my graduate students and I have been working in central Georgia for the last several years, and we realized it was not a simple process. It simply did not pull straight out. Next. One of the things that happened was, here's another magnetic map. This one's not colored, but you can see these straight lines in here. These are dikes. These are planar, not very thick layers of magma that shot through the crust and crystallized, okay? Next. they're all, what I showed you was an area right in here, but they're present all the way around the Atlantic. In Africa, as I said, North America, and they're present in South America also. They have different orientations. Sorry, Dave.
Sort of cracks then that allows the magma to come up with all of the stresses going on?
Well, what that tells us is it's a very systematic breakup that occurred that produced these dikes. Okay, they have to be tension cracks. That is pull-aparts, okay? The interesting thing about the dikes is the magma was uncontaminated as it came through the crust. So let's go to the next one. And this is North America again, or Eastern North America. We have two sets of these things, but these in the Southern Appalachians are straight northwest oriented. We don't have any in Tennessee, but they're in the Piedmont, and then they do get up into the valley of Pennsylvania a little bit. Next. If you look at one of these dikes, this one in Georgia, this thing's what, about 15, 20 feet wide? Some of them are narrower than that, some of them are wider than that. But they have no chemical contamination in them. There's no crustal contamination of the materials that they came through. You break one of these boulders open, this is weathered of course, that's what it looks like, beautiful fresh rock. Absolutely beautiful. Next. If you look at it on the microscope, absolutely pristine, original dark minerals that we see in these kinds of rocks. They should be contaminated, but they're not. Next. So I asked myself, okay, how fast would one of these dikes have to propagate to keep it from being contaminated, also to keep it molten while it goes through the crust and not solidify, not lose its heat, because there's a tremendous surface area. Well, so I found an equation, or a relatively simple equation. This is Young's modulus, this is density, and so on. And so you can estimate, assuming density of 2.65, which is the crust of granitic crust, I estimate a velocity maximum of 210 meters per second as a crack propagates through the crust then. How long does it take to do this? 3 minutes. This occurred at 200 million years ago. So I jokingly say, well, maybe some of the dinosaurs went extinct at that time if they were standing near one of them. Whiplash got them. Next. Okay. So again, what we have learned recently in this area down here just south of Atlanta. Next. This is a map that's been compiled by one of my PhD students right now, Matt Hubner. We've worked on a number of big faults in the Georgia Piedmont, and this one is very interesting because it got reactivated, not like the Brevard at all, but it first moved right lateral, and then it moved the other way. And we don't know why it went the other way, but this is when Pangea was breaking up. And there were some other little faults up in here that formed at the same time as this one was reactivated. Next. So you look at some of the materials in the fault zone in the field. It's very silicious material, so it's resistant to erosion. Next. And if you look at it in a hand specimen, it's all cracked up, and you can see healed cracks all through. It's almost all quartz. Next. You also have this kind of thing here, which is ductily plastic deformed material. It's not brittle at all. We don't know how it connects to these things I just showed you. Next. If you look at them on the microscope, you can see this is the brittle stuff here. This is the plastic material here. All quartz on both of them. And we don't know how these two are related to each other. In my opinion, they had to form about the same time, though. Next. So what we've done is to break up Pangea, not in a simple pull-apart way. Finally, it's settled down. It's separating very uniformly out to the mid-Atlantic ridge is out here somewhere. Very uniform magnetic stripes out in the Atlantic. And everything worked pretty well. Next. So here's our present-day continental margin. And this is a cross-section that we're drawing actually all the way across the United States. I call it the I-40 section because it roughly follows I-40. Modern ocean crust out here, very old crust in the interior, Appalachian crust in here. Next, and the doubling of the crust occurred at that time, then before, as Pangea formed before it broke up. Finally, the question of how old the present-day topography is, okay? When we took 7th or 8th grade geography, perhaps even courses in college, we were taught the Appalachians are the oldest mountain chain on Earth, okay? So let's look at some information about that next. These are digital elevation models that anybody can have access to online. Here are the Appalachians from Nova Scotia, actually, and Quebec, all the way down through New England. The Adirondacks are there and on down into Alabama. Talking about old topography, that's right, these are the Laurentian Mountains on St. Lawrence River. The topography here may be older than this, but it may not be. And this is, here is Pennsylvania, New York in this area. So we're looking at the southern part in here. Now the thing I'd like to show you is, look carefully. We've been looking at structure that goes all the way through of the same kind, okay? This is the outer part of the Appalachians. And these wrinkles, folds, faults that come up through here. Oop. Okay, what I want to show you, we got to go back, zoom out, please. Okay. The high topography, which are these brown and red colors, is, as you know, is in the Smokies, in this area. It dies out down into Georgia, still some high topography into Alabama, not very high. Then followed up through North Carolina, Tennessee, into Virginia, and the high topography shifts over into the valley of Virginia. Why? We don't know. But it can't be related to the original shapes of things that were produced 300 million years ago. Okay? So this high topography shouldn't even be here. Here's the Blue Ridge. Same rocks as down here, essentially. Continues up into here and finally dies in Pennsylvania at South Mountain. It's a bunch of low hills. So, okay, let's go to the next one. All right, here's our nice Blue Ridge, and this is off the Blue Ridge Parkway in North Carolina. This is looking off of Clingman's Dome. Mount LeConte is either this one or this one, I can't remember which. But this is all the rugged topography we have down in the south. Now, next. Rivers. Okay, well, here's our high topography we just talked about. If you look at the rivers that are that drain into East Tennessee and into Virginia, they drain all the way across the Blue Ridge. How those rivers cut their way across the Blue Ridge? Their headwaters are over on the east side. Actually, the Little Tennessee, which is this one, goes all the way out from Georgia up into North Carolina, then westward into Tennessee. The New River up here starts in North Carolina, drains northward into Virginia, then west and becomes the Kanawha, and eventually makes it into the Ohio. Okay? And you can go through any of these rivers you want to. Same relationship occurs. How do these rivers cut their channels? Why would a river originate on the east side of the Blue Ridge and cut a channel there? Today's rivers are cutting headwater, they're eroding headward and draining into the Atlantic. Of course, these are draining still into the Ohio and then into the Gulf of Mexico. Next. Okay, here are our streams again I was just talking about. There's something else up in upper East Tennessee. If you haven't been up there, go to the Great Fossil Site sometime. Okay?
Doesn't that basically mean that the rivers had to be there before the mountains?
Exactly. Yeah, before the uplift occurred.
Yeah.
These are not 300-million-year-old rivers. Okay? So I'll write you a check later, Dave. Okay. Great Fossil Site up near Johnson City. Next. These are some of the fossils that have come out of there. I don't know if it was the rhinoceros or the crocodilian, but it told them, one of these fossils said, this is a 7-million-year-old place. It was a lake 7 million years ago. Well, lakes don't occur on hilltops, right? Today, next, if we can see this, here's the gray site, where right there. here's a stream that drains, I don't know whether it goes this way or that way, I think it goes this way. But the grave site sits on a hilltop right now. How did it get there? It was 200 or 300 feet above the adjacent drainages. That means there's been 200 to 300 feet of uplift just right there locally in the last 7 million years. Okay, next. And this kind of material we don't know the age of it. That's why I've got a big question mark there. But this material I got in Alabama, but it occurs in South Carolina. This was in the Piedmont in Alabama, not in the coastal plain. You see this in the coastal plain in South Carolina, Georgia, and in the Piedmont and other places. You see this in the coastal plain of Alabama too. And we think this is about the same age material. And we think this might have covered the entire Piedmont before 7 million years ago. We don't know that. That's speculation. Next. Very difficult to see this one, but this is a geologic map of part of the Bearden, Tennessee quadrangle, West Knoxville, what used to be West Knoxville. But here's the Tennessee River down here, okay? If you go into this area, of course this is subdivisions down here today. There are gravels that sit on the hilltops right there, 400 feet above the Tennessee River. In the time that the Tennessee River has been there, it's cut down 400 feet. And that tells you the Tennessee River itself is a fairly old stream. Of course, it cuts through the plateau also, in the same way we're talking about these Blue Ridge streams cutting through. Again, the drainage had to be there beforehand, okay? Next. This is what some of this gravel on the hilltop, a place called Rocky Hill in West Knoxville, is. And the normal bedrock here would produce a valley. It's a limestone. Here we have a ridge there held up with these gravels. Next. Okay, and then if you look at the truncation of the Appalachians here in Alabama where it's exposed, and on up, but here in Alabama in particular, you see the trends of the Appalachians coming right down through here and they're truncated. And the elevation of this line right here, the truncation line, is I think 300 to 400 feet, 500 feet in this area. Okay, not very far to the northeast, in North Carolina, Tennessee, what you got 6,000 foot mountains. How does this occur? Well, that means uplift probably occurred up here, long after this boundary formed. Okay, the truncation occurred 100 million years ago, maybe longer. Next. Other information, this is from the guy who knows all this stuff, got in his head and he hadn't published it. This is out of an abstract or two. But there are little bits and pieces of young sediments. I showed you a piece of what could be young sediment. But at elevations of 2,200 feet in North Carolina and Tennessee, and above 1,000 feet in places in the Piedmont, that'd be in Georgia. And so indicate these sediments once covered a lot of the Appalachian crust, but now been eroded, probably post 7 million years ago. So, again, this is other information. There is still other information out there. Next. So here are Snowbird Mountains. You use any example you want. 6,000 foot crust there. These are 6,500 foot mountains in southern Poland, part of the Carpathian chain. And these are young mountains, of course, but they're only about 6,000 feet, 6,500 feet high. They have a timberline, 49 degrees latitude versus 36. Next. Go to Brazil. If you look, we got this off Google Earth today. You can do this tomorrow if you want to, or tonight if you'd like. Here is Rio de Janeiro, Sao Paulo, and then some of the other areas to the south as you head down toward Argentina. There are mountains all in here. These are not young mountains formed like the Carpathians or the Alps or the mountains in the western North America. These are mountains formed on old rocks. There's no plate boundary there to form the uplift and this sort of thing that we have in the western U.S. or western South America. So again, this is the same phenomenon we're seeing in the Appalachians, except this is smack up against the coast. Next. Why do we have mountains like this here? This is in Rio de Janeiro. This is the Cristo de Corcovado, perhaps the largest mountain in this area. There's the Palo de Azucar in Rio de Janeiro. You have mountains right up on the coast there. Next. If you go to the west coast of Norway, and interestingly, this is the west coast of Norway here. Oslo sits right there. You can't read it on the map. That's located there. Stockholm, Sweden is over there. This is the Gulf of Bothnia. And the only reason this is there because glaciers loaded the crust there and made it sink. And it's rebounding now. It's emptying the Gulf of Bothnia. But this area is high. And this is the North Sea coast, or eventually becomes the Atlantic coast. So why are there mountains here? These are 7,000-foot mountains developed on old rocks again. Next. If you look at, this is what the topography looks like in that area. This is some of the fjord land. This is the Jotunheim, part of Jotunheim National Park. Very beautiful country. Next. And you go to the northwest highlands of Scotland up here, and throughout most of the northern part of Britain and Northern Ireland, you have topography like this. And in Wales down here as well, you have mountains. So this is the Stock of Glencool in Scotland. I don't know where this is. I got this off the web, but it's a very nice mountainous country. Old rocks. No plate boundaries there today. Next. So, are we looking at the world's oldest mountains? Emphatically, no. That's my opinion. Next. So, what's the mechanism? What caused all this? Well, there was a paper published by a guy that I knew named Paul Roper in 1980 in a journal called Tectonophysics. And this is 180 million years ago, a mid-ocean ridge spreading. The Atlantic was opening. You had subduction zone off western North America. And then 143 million years ago or so, you had sediment from the erosion of the Appalachians accumulating out here. And what he was saying is the load of the sediments itself may have caused the uplift of the Appalachians here at that time. I think mathematically you can show that that would not work. There's not enough load there. But this is something that we have not done, but you've got to realize that as ocean crust forms and ages, it gets denser. And so the reason we have such deep ocean just off eastern North America is because this is very old ocean crust out here. So that may have an effect of this loading and then down and up effect called isostasy. Can't all be isostatic though. It's got to have something to do with the deep circulation in the mantle as well. Next. So in conclusion, the Appalachians formed by 3 big tectonic events way back, and breaking up Rodinia and then forming Pangaea. And then Pangaea broke up and led to the formation of the modern Atlantic. And then present-day topography on all sides of the Atlantic is likely very young. So to me, this is a great opportunity for future research. Next. So a brief commercial message here. There is a display over in McClellan Museum right now comparing the Appalachians to the Himalayas. The museum staff did a fantastic job of putting this together. We did a lot of work to give them materials to put in it, but they did all the work in putting it together. It's really worth going over there to look at. The display will be up until May 20th, I think. Yes?
Speaking of the Himalayas, I've been told that the Appalachians at their maximum extent were taller than the Himalayas.
They could have been. We don't know for certain. They could have been higher than the Himalayas are today, yeah. Yeah, but there was a double crust here, just like there today is a double crust. The thickest crust in the world is under the Himalayas and the Tibetan Plateau, 70 kilometers, 75 kilometers. Right now, under us right here is a 50-kilometer crust. We don't know why that's still 50 kilometers thick either.
And that's deformation, that's not folding over and doubling, that's just...
No, that's the bulldozer, the snowplow effect that occurred in 280 million years ago, 260, okay? That's in the Appalachians. In Himalayas, that's going on today.
And
Sure.
That jet of rock that came up at 200 meters a second,
Yeah.
is that when the
That's-
first crack appeared?
That is when the fractures, a whole array of fractures occurred up and down the east coast of North America and Western Africa. The continents were still together. They had not separated yet. And so the crust started to fracture, and you got these dikes shooting through there. Not at the same instantaneous time, but probably over a period of hundreds of thousands to a few million years.
I was wondering if anyone had ever done a back of the envelope on the energy release of that much rock going that fast, megaton equivalents.
Well, I don't think it, again, compare that to the mass of the crust, and it would be significant, but I don't know that that's, I don't know that anyone's done the calculation, and I don't know that it would, well, again, I'm guessing. Intuitively, I wouldn't think it would be that significant, but it could have been. That's why the joking thing about killing some dinosaurs off about that time. Yeah.
That's a reasonable fraction of the speed of sound. You find any shock structures along there?
No, no. We're not seeing, we don't see shocked quartz in the way that you would in a meteorite impact. That's a totally different ballgame. You've got a bolide that travels at thousands of kilometers per second. This is not that fast at all. And there's the energy difference is tremendous. But of course, a bolide, by comparison, is relatively, well, some of them are large, but they don't cover a very large area when they impact. Yes?
Are there any places on Earth now where some of these dikes may be forming? Or?
Yes. Again, you don't see them come to the surface most of the time. And well, of course, we see dikes in Hawaii. And of course, some of the lava that comes out of Kilauea is not coming out of a single a pipe or anything like that. It's coming up a crack. But in terms of cracking continental crust, I don't know of any place in the world, unless you can see it in the rift valleys of Africa, where that's an active breaking apart rift zone there. So eventually, the East African area on the east side of the rift zone will pull apart and move out into the Indian Ocean, just as the Red Sea is moving apart today, too.
You don't see that in the spreading zones under the ocean.
Oh, yes, you do. You have lots of dikes there. Yeah, that, as a matter of fact, one of the characteristics, the attributes of new ocean crust and spreading is you have myriads of dikes forming as part of the upper part of the oceanic crust sequence, the part that's right below the lava sequence there on the surface. Yeah.
If we watch Yellowstone region with sonic monitors, what do we see?
Well, you see an area down below of a single magma chamber that's still active, and of course not producing volcanic eruption at the surface, but it did in the past, because that's what the Snake River Plain is. And as you go down the Snake River, all of the basalt, all the big lava flows in there, and then the Columbia Plateau is even older. Has lava flows all over.
There were enormous eruptions in all of sort of eastern Washington, weren't there?
That's the Columbia Plateau, yeah. Mm-hmm. Yeah. Okay, next. There's just a couple left, yeah. So you get the idea that maybe I have a distorted point of view of things. Next. And my graduate student, this is Matt, my PhD student. Got to have to juggle a lot for me. And so I'll leave you one more thing next. Whether this is a sleeper or a howler, you could decide for yourself. So thank you very much for your attention.
I get a feeling from this just enormous quantity of data, information and data you've shown us, that we could be at the start of some sort of a new age of being able to create mathematical models of the entire process of mountain building. And that if we get those, check them out on the Earth and start applying them to what we can visualize, what we see on Venus and we will see on Mars. It's just a nice start of a new age.
Well, some people say that if you get a lot of data, it messes up the mathematical models. And,
Too bad.
but no, you're right. The problem is that you need larger and larger computers to be able to do this. And one of the things that I was disappointed about when they put in the supercomputer, it gets more super every year at the lab, is they made a conscious decision to not work on solid earth problems. They said, we want to work on climate and other things like that, so, which is fine, okay? But the Japanese, with their supercomputers, one of the things they have done from the very beginning is to try to model earthquakes and tectonic features. And of course, they're sitting right on top of it there. There's a very good reason for them to do so, in addition to climate. Yeah. Yeah. Other questions?
Yeah.
Yes.
Yeah,
John?
and this may have been asked earlier, but I couldn't hear from back there. But I had heard that the Smokies were once taller than the Rockies. And more than that, taller than the Rockies will ever be. I don't know.
Possibly.
Possible.
Possibly. We don't have a way of.
Smokies ever were.
Well, we have ways of estimating what the thickness of the material was there by looking at the present day exposed rocks and what kind of metamorphic minerals they have in them, because that's the higher temperature, the higher the temperature to which the rocks were affected, subjected, indicates deeper and deeper burial. And so by the time you're on the east side of the Smokies, you've got some pretty high-grade rocks. But all that metamorphism occurred at 460. It did not occur during the collision.
Okay.
Yeah, and so we don't really know exactly how much material there was there. We're guessing when we say that there might have been 10 kilometers more, 30,000 feet of material above there. That would get, you don't produce much metamorphism with 10 kilometers. Mm-hmm. Yes?
You want to say anything about Stone Mountain, Georgia?
It's an isolated remnant of that the drainages around there simply didn't cut it down, because the granite that makes up Stone Mountain is much more extensive than the mountain itself. People think it's a granite body itself. It's not. There's a larger body that goes several miles out from Stone Mountain. As a matter of fact, that's what they quarry for a lot of the stone used in the Atlanta area. And Emory has a lot of buildings built out of Stone Mountain granite. They wouldn't have quarried Stone Mountain to do that. There are other sources around it. Yes?
Just north and west of here are what we call the Cumberland Mountains.
Uh-huh.
Are they considered part of the Appalachians? Because
Sure,
the structure-
sure.
You can see I've worked in there many, many years, and I see I'm interested in the biological part of the mountain.
Uh-huh.
The coal and all that.
No,
It pours on an awful lot of sedimentary stuff.
yeah, but the sediments are derived from the Appalachians. That was part of the great delta that formed. It was from sediment shed off the rising Appalachians at 300 to 260 million years ago. And
We're being told that they were formed by erosion through those.
well, that's true. That's what happened in the last few million years.
Okay.
Again, you've got to divorce yourself from the topography from the rocks themselves. This is my message, I guess, if I had one.
Like you were saying that our Appalachians down here were at one time the same as the flat part up in Virginia. Is that?
No, not the flat part. Those rocks are tilted up there too, and in West Virginia. But it doesn't matter. The high topography is the key.
That's
Okay.
what I'm saying.
Yeah.
I didn't say.
Yeah. The high topography.
Maybe I'm not understanding how top.
Well, the high topography is the high mountains. Okay.
Okay.
The high mountains are down in Tennessee and North Carolina, and then they shift over into rocks where they shouldn't be, in my opinion, sandstones and limestones, as you go into Virginia. Well, the high mountains really ought to stay over in all these hard rocks that we have in the Blue Ridge.
Oh, I
But it doesn't.
misunderstood. I'm sorry.
It doesn't. No, it's okay.
But
But,
isn't that mostly artificial limestone?
no, it's got a lot of other stuff in there too. That's what holds the ridges up. The thing that holds up Clinch Mountain, the sandstone, that actually Clinch Mountain goes up into Virginia, and then it starts to be repeated as you get up into central Virginia, goes all the way into Pennsylvania. When you fly over Pennsylvania, you see these beautiful zigzag ridges. That's the same sandstone as we have ending right here at House Mountain in northeast Knox County. Yeah.
As long as continuous. United States, isn't it?
I don't know. I don't know. Yes?
That granite from Stone Mountain, does that extend down to Arabia Mountain? In
No.
southeast?
That's a different granite.
It is?
We dated that, the one at Arabia Mountain a couple of years ago. We know its age is much older than the Stone Mountain granite. Stone Mountain granite is about 300 million years old. Okay, the Arabia Mountain area, that's, again, that's called the Lithonia granite or Lithonia gneiss, and it's 400-something million years old. Yeah, we actually, and there's a recent date on the Stone Mountain too that came out this past year that, again, reconfirms the young age of the Stone Mountain. Well, I very much appreciate your attention this evening.